So let me mention two things that I forgot about these three bosons, this abelian affine algebra. So the constructions I showed can be generalized to non-abelian algebras. So I would like to give the names of these generalizations. So the construction of the energy momentum tensor from the current has a generalization to the non-abelian case called the Sugawara construction, except that in the Sugawara construction, you don't have this derivative term. And the equations that we obtained, the first-order differential equations for the correlation functions, have a generalizations. They are called Knizhnik-Zamotchikov equations in the non-abelian context. Okay. So now let's talk about the conformal bootstrap, and that's the third part of these lectures. So far, all the equations we obtained for correlation functions, so the word identities, the Belyavin-Polyakov-Zamotchikov equations, were linear equations. So they are the consequences of symmetries, but they don't allow you to completely compute the correlation functions. For that, we need nonlinear equations. So now I'll start to introduce extra axioms that will lead to nonlinear equations. And the first axiom is the single-valuedness of correlation functions. So correlation functions are single-valued as functions of z, of the positions. So now let's see what this axiom implies for a two-point function. So let me remind you the form of the two-point function. So this is proportional to delta 1, delta 2, z1 minus z2 to the minus 2 delta 1. So if I want this to be single-valued, I need delta 1 half integer. Well, I mean, this is not a very good situation. I mean, it's in conformal fields, in interesting conformal field series, we have dimensions that are not half integer. So what's missing is actually some dependence on z bar, because the functions I would like to have are things like z1 minus z2 to minus 2 delta 1, z1 bar minus z2 bar to the minus 2 delta 1. So that's just the modulus of z1 minus z2 to minus 4 delta 1. And that would be single-valued for any value of the conformal dimension delta 1. So if I want this axiom to be valid in interesting cases, I have to add dependence on z bar. And to do that, I will assume that my symmetry algebra is not just the Virasoro algebra, but two copies of the Virasoro algebra. So I would have a Virasoro on the left and an Virasoro bar on the right. So Virasoro on the left is what we have seen until now, and it gives you differential equations of the type d by dz. And the right-moving now Virasoro algebra would give exactly the same equations, but for z replaced by z bar. So now, if I'm assuming that these fields are primary fields with respect to both left and right algebra, and they have the same dimension on the left and on the right, then indeed their two-point function looks like this, and I can have arbitrary conformal dimensions. But actually, I'm not even restricted to having the same dimensions on the left and on the right. So let me write a more general two-point function for fields that have arbitrary left and right dimensions. So delta 1 bar is the right dimension, v delta 2 bar. So that would be by the word identities, delta 1, delta 2, delta 1 bar, delta 2 bar, z1 minus z2 minus 2 delta 1, z1 bar minus z2 bar minus 2 delta 1 bar. So actually, the condition for this to be single-valued is that delta I minus delta I bar is half integer. So, okay, so of course, the special case when delta equals delta bar is quite interesting, and it's called the diagonal case. So I would define a diagonal primary field as a field which is primary for the left and the right algebras. And that has the same dimensions on the left and on the right. And a diagonal conformal field theory is a CFT where all primaries are diagonal. But so most of our examples will be diagonal conformal field series, but in some minimal models, we will consider also non-diagonal series. So that's...
so in that and delta var, they also have interpretation just in SL2, so in terms of Lorentz theory, no?
You mean with respect to the global symmetry?
Yes, with respect to the global symmetry.
Yeah, with respect to the global symmetry, well, I mean, all this is true also if you have just global symmetry. Yes, you can have a left and right moving conformal dimensions. Yes, if you want, I'm complexifying this symmetry algebra, the Virasoro algebra. That's why I'm split. That's what allows me to split it into this product. And similarly, if you take your SL2C global symmetry algebra and you complexify it, you just get SL2C left times SL2C right. And yeah. So, okay, so now we have done this, we have these two algebras, and yeah, all the axioms that we had for the left are also true for the right, and in particular, d by dz bar acting on any field should be L minus 1 bar acting on this field. Now you might worry about what I want to interpret as conformal symmetry. I mean, conformal symmetry should be just one Virasoro algebra, not a product of two Virasoro algebra. So the generators of conformal symmetry in this case will be identified as Ln plus Ln bar, just because they should act the same on Z and Z bar. I mean, Z bar is always the complex conjugate of Z, so they should transform in the same way under conformal transformations.
So we can have descendants that have different conformal dimension, delta and delta bar.
Yeah, the question is whether descendants can have different conformal dimensions, and yes, the answer is yes. So you can start with a primary field. Let's say we start with a diagonal primary field. So actually, let me call V delta of Z. Now, if I write V delta of Z, implicitly it means a diagonal primary field with the same dimensions on the left and on the right. So we can start with this one, and we can write descendants of the type, let's say, L minus 1, L minus 2 bar, L minus 3 bar of this V delta of Z. So this descendant on the left will have dimension delta plus 1, and on the right, it has dimension delta plus 5. So it's really the primaries that should have the same dimension for the theory to be diagonal, but you will also always have descendants with spin. Actually, the difference between delta and delta bar, if you want, is called the conformal spin. Okay. So that's all for the moment about single-valuedness of correlation functions. So the axiom is that correlation functions are single-valued, and yeah, we derived some consequence of this. Well, yes?
So if you have like different descendants, will those correlation functions be also single-valued? Because
Yes, essentially, yeah. No, that's a good question. Will correlation functions remain single-valued if I consider dissonance like that? The answer is essentially yes. For example, if you consider a d by d, L minus 1, so that's d by dz1, acting on my correlation function, which is, well, let me write it as z1 minus z2 to the minus 4 delta 1. So essentially, I will get minus 2 delta 1 over z1 minus z2 times my correlation function. So I will get this prefactor, but this prefactor itself is single-valued. And it works the same for the other operators. They don't act just as derivatives, but as more complicated differential operators inside the correlation function. But always I get some single-valued prefactors of this type. Okay, so now let me continue with another powerful axiom. The existence of an operator product expansion. So now, I mean, this will be, I mean, the rest of this lecture might be the most difficult and maybe the most important part of this series of lectures, because I will introduce the crucial ideas of the bootstrap. I will define conformal blocks and crossing symmetry. I'm not sure they are the funniest part of the lectures, but probably the most important. I mean, what's funny is to use that in specific models, which we will do later. But now it's time to wake up. I mean, now it's time to have your sugar injection or adrenaline or whatever. It would be a perfect time for a fire exercise drill, actually, but I mean, I don't think it could be organized. So let's define operator product expansions. So that's really a nonlinear axiom in contrast to all these symmetry conditions. So this nonlinear axiom starts with two fields, and let me write them as fields corresponding to states. So V1 of Z1, V2 of Z2, and I want to rewrite this as a linear combination of fields. So which fields? Well, some fields VI of Z2, where, so VI now is supposed to be a basis of the space of states, basis of the spectrum. So I'm summing over this basis and putting some coefficients. C, let me call them, well, C, V1, V2, Vi, coefficients which depend on Z1 and Z2. So this axiom takes two fields and replaces them with a linear combination of fields. And this is supposed to be true when Z1 is close enough to Z2. So how close depends on the correlation function which you are considering. So these coefficients, well, let's call them the OP coefficients. Okay, so now let me say why this axiom is very powerful. So let's assume we know the operator product expansion, not just that it exists, but let's assume we even know the coefficients. Then if we have an n-point function to compute, well, we can just use the operator product expansion for the first two fields and reduce it to an n-1 point function. And we can use further operator product expansions until we reach, let's say, a 2-point function. And 2-point functions are essentially trivial by conformal symmetry. So if we know the operator product expansion, we can compute any correlation function, basically. Now, the question is, can we determine this operator product expansion, and can we compute these OPE coefficients? So I will examine this question in the case of primary fields to be simple. So I'm starting with two primary fields, V delta 1, Z1, V delta 2, Z2. And then the problem is I can't just have primary fields here. I have to sum over all the fields in the spectrum. I have to sum over a basis of the spectrum. So let's nevertheless assume that on the right-hand side I have primary fields and some descendant fields. So I'm grouping fields by some primary and some descendants. So of course I will have a sum over delta, a sum over different possible primaries. The sum of the descendants is written here with these dots. And then I will get some coefficients. Now it's time to use a bit the conformal symmetry to constrain these coefficients.
Sorry, but this relation, if we have an actional dynamics in the field, this relation should be true on shell or off shell?
The question is whether this relation is true on shell or off shell.
Because if it is true off shell, in the action you can just substitute any quadratic expression in the fields with just the linear one. So.
Yeah, you fear that if it was true off shell, you would trivialize the theory, basically. Yeah. Okay, no, that's a good question. I really can't answer right now. Especially, I mean, this is true even if you don't have any action. So what happens if you have an action is not too clear, yeah, to me. Okay, so now let's constrain the OP coefficients by using conformal symmetry. So in the same way as we can derive word identities for correlation functions, we can have word identities for operator product expansions which constrain these coefficients. Well, just as in correlation functions, the first word identity is translation invariance. And you could guess that this coefficient has to be a function not of individually Z1 and Z2, but of Z1 minus Z2 by translation invariance. And there is another word identity which tells you even that it is some power of Z1 minus Z2. And this power must be now let's have diagonal fields, and the power must be 2 delta minus delta 1 minus delta 2. So that's a consequence of dilation symmetry. So translation and dilation symmetry determine the dependence of the OP coefficients on Z1 and Z2 in the case of primary fields. And we are left with a coefficient here which does not depend on Z1 and Z2, but which only depends on the dimensions delta 1, delta 2, and delta. Okay, so now these translation and dilation invariants were, if you want, the global word identities for operator product expansions, and you also have local word identities, and these local word identities allow you to determine the contributions of descendants if you know the contributions of primary fields. And there is an exercise about that. The exercise is to determine the contribution of the first descendant. So the first descendant is L minus 1, V delta. Well, why is this the first? I mean, we have another right-moving descendant at level 1, so let's consider both of them. And you can find that the coefficient here should be delta plus delta 1 minus delta 2 over 2 delta. And here, well, the same coefficient. And here is a Z1, 2 prefactor. Here is a Z1, 2 bar prefactor. And the next corrections are of order Z1, 2 squared. So that's a consequence of local word identities for operator product expansions. But actually, you can, in principle, determine all the subsequent terms if you know the coefficient of the primary field. So as in correlation functions, primaries control the behavior of descendants. Okay, next, let's take this operator product expansion and insert it into a 3-point correlation function. Ah, yes.
Okay, I was going to make a comment, but probably that's what you were going to say. What you wrote down is using global word identities. I'm going to say that if you insert this inside a 3-point function, you might as well match with the answer that is already fixed by conformal symmetry, and this will constrain for you the format, whatever it is.
Yes, so indeed I want to insert it into so you want to insert it into a 3-point function to constrain the form of this sum. You can do that. It's not the simplest way of constraining it. Actually, I want to insert it into a 3-point function to determine this quantity, to relate this quantity to the 3-point function. So I'm inserting, if we insert it into a 3-point function, and if we assume that the 2-point function comes with a coefficient 1, so let's assume the 2-point function is of this type, delta 1, delta 2, z1 minus z2 minus 4 delta 1. So now I'm assuming the coefficient here is 1. I mean, I can do that by renormalizing my fields if I need to. Then, if I insert the operator product of my first two fields into a 3-point function, well, I should obtain a sum over delta of C delta 1, delta 2, delta, and, well, of course, Z1 minus Z2, 2 delta 1, 2 delta minus delta 1 minus delta 2, times the 2-point function. So I reduce my 3-point function to a 2-point function of V delta of Z2 with V delta 3 of Z3, plus corrections. This order Z1, 2 corrections. On the other hand, I know that my 3-point function should be given by Z1, 2 to the delta 1 minus delta 2 minus delta 3, Z1, 3, delta 2 minus delta 1 minus delta 3, Z2, 3, delta 1 minus delta 2 minus delta 3, up to some coefficient. And if you do this exercise, you will find that the coefficient here should be nothing but this coefficient here from the operator product expansion. C delta 1, delta 2, delta 3. So therefore, this coefficient is called the 3-point structure constant. Yes?
Is valid only for the diagonal case? I'm sort of missing the barred weights.
The question is whether this is true only for the diagonal case. The answer is no, it's true for even the non-diagonal case. But somehow I'm, yeah, indeed, here I should, if we are in, I mean, first, even if we're in the diagonal case, I should write modulus squared like that to take into account the right movers. But we could also do it in a non-diagonal case, and again, this coefficient of the operator product expansion would be related to the 3-point structure constant, would be the same.
There's the Z bar 1, 2 in the first.
Yeah, there is a Z bar 1, 2 here.
It goes with unbarred weights. Is that correct?
Yes, I mean, here is written really for a diagonal theory.
Okay.
But if it was non-diagonal, I would have delta bar here, you're right. So now, let's compute 4-point functions then. Well, we'll stop at 4-point functions again, and actually we'll have good reasons to stop at 4-point functions. But for the moment, let's try to compute a 4-point function. So which 4-point function? Well, now I'm going to send, in order to simplify notations, I'm sending fields to Z, 0, 1, infinity, and 1. And I'm using the operator product expansion of the first two fields. So I have a sum over some dimension delta of C delta 1, delta 2, delta, z12 to the 2 delta minus delta 1 minus delta 2 times a 3-point function v delta of 0, v delta 3 of infinity, v delta 4 of 1. Plus descendants. I could write it like that, 1 plus order z1, 2. Now, what is this 3-point function? Well, now we know it. It has to be proportional to a 3-point structure constant, C delta 3, delta, delta 3, delta 4. And since the fields are 0, infinity, and 1, I mean, there is no z dependence at all, so it's just a 3-point structure constant. So therefore, the 4-point function is a sum over delta of C delta 1, delta 2, delta, C delta, delta 3, delta 4. Oh, sorry, it's not z1, 2 now, it's just z, because z1 is z and z2 is 0, so it's just d to this power. Z to the power 2 delta minus delta 1 minus delta 2, 1 plus order z1, order z now. Now z1, 2 is just z. So this order z hides infinitely many terms, the contributions of descendants. But the symmetry algebra factorizes into left-moving algebra and right-moving algebras, and the contribution of descendants also factorize into z-bar dependent contributions corresponding to the left-moving descendants. Z-dependent for the left movers and z-bar dependent for the right movers. So the point is that this whole expression is factorized. It can be factorized into some function f delta s of z times the same function of z bar. Now, this f delta s is by definition a 4-point conformal block. So it is the sum of the contributions of descendants to a 4-point function. So if you want a normalized, so that it starts with a 1. So it's if you want a normalized sum over descendants. So it's a function, of course, it doesn't just depend on delta, it depends also on delta 1, delta 2, delta 3, delta 4. It also depends on the central charge. So it's a pretty complicated function, but in principle, you know it. I mean, from word identities, you should be able to compute it, although the computations are complicated. If you want, it's a universal function. It's just like the character of a representation. It's entirely determined by symmetry. So determined by symmetry. Well, actually, the analogy with character is more than an analogy. If you want, a character is just a 0-point conformal block on the torus. Okay. Well, what are the properties of these conformal blocks? Well, I will not give many properties, but well, the first property that we can see from the very definition is that it has to start with z to the power delta minus delta 1 minus delta 2. And then you have a power series in z. And well, actually, let me give the first non-trivial term of this power series. So the first non-trivial term, well, it starts with delta plus delta 1 minus delta 2 over 2 delta, just because when you did the operator product expansion, that was the coefficient of the first correction. And then you have delta plus delta 4 minus delta 3 times z now plus order z squared. So again, it's an exercise to compute this first term. Well, the first term actually doesn't depend on the central charge, but the second term already depends on the central charge. Okay, so are there questions on conformal blocks? Yes?
The statement about factorization is not very obvious because when you write down the sentence, you can have left movers and right movers products, right?
Yeah, so you're saying the statement about factorization of conformal blocks here is not completely obvious. Well, I think still it's relatively straightforward if you think about it, because I mean your symmetry algebra is factorized, your representations are factorized by definition. I mean, I'm considering a Verma module, I'm considering a primary field that's both left and right primary, so the whole representation is factorized. So the word identities are factorized. You have independent left and right moving word identities, and these blocks are completely determined by word identities. So I think if you do this exercise, basically you can see, even at the first order why it has to be factorized. So another question?
So you said axiom correlation functions are single value, and now this thing is not single value, so it does not propagate down.
So you're worried that conformal blocks are not single valued, although correlation functions should be single valued, right? And I mean, you're right if that's the question. You're right, indeed. You cannot take any combination of conformal blocks and call it a correlation function. Single valuedness of the correlation function will give you very strong constraints on which conformal blocks you can combine. And we will see that in the next lecture.
And just this example, there is z to the delta minus delta 1 minus delta 2.
Yes?
Plug that into that one. Should there be a minus sign in the exponent somewhere?
Should it be a minus sign? Where would you want to be a minus sign? In this exponent?
Yeah, like an overall minus sign.
No, I mean, unless there's a mistake somewhere, I mean, this should really be delta minus delta 1 minus delta 2. Yeah. So, to finish this lecture, let me talk about crossing symmetry. So I have, to compute this 4-point function, I have used the operator product expansion of the first and the second field. But I could have used another operator product expansion of, let's say, the second and the third field. And the result would not be obviously the same. It would actually look a bit different. So let's write it. So the same 4-point function can be written. Well, let me rewrite actually the S-channel. So this is called the S-channel decomposition. So that's a S-channel conformal block. So the S-channel decomposition looks like something like sum over, now I'm calling it S, CS12, CS34, times the conformal block, and the traditional notation for this block is this, 1, 2, 3, 4. Well, here I'm using this notation for actually the product of the left and right moving blocks. And now, if I was doing the operator product expansion between the second and the third field, I would call what propagates here the T-channel dimension, and I would have a sum over T of C T23, C T14, times some T-channel blocks. So what are T-channel blocks? Well, they are a generalization of the definition of S-channel blocks, except that you start with another operator product expansion. So in particular, the T-channel block looks as follows when Z now, so that was the behavior of the S-channel block when Z goes to 0, but the T-channel block has a natural expansion when Z goes to 1. And this expansion is 1 minus Z to the delta minus delta 1 minus delta 4, 1 plus something of order Z minus 1. And again, it's completely determined by symmetry. So we have this equation which relates the S-channel and T-channel decompositions. Well, we are summing this S-channel dimension over, let's say, the spectrum, big S. The T-channel dimensions also are summed over the dimensions that appear in the spectrum. So now I'm understanding the spectrum as a set of dimensions. So S equals set of dimensions. And we have this equality, which now you can view as a nonlinear equation for the structure constants. Well, that's assuming you know the spectrum. Or you can view it as a constraint for both the spectrum and the structure constant C. So that's called crossing symmetry, this equation. So it's an equation for the spectrum S and the 3-point structure constant C. And it turns out that if you have a solution of this crossing symmetry equation, then you can compute any n-point function. I mean, you could also consider n-point functions and start decomposing them using operator product expansions. You have many ways of decomposing the same n-point function, but all these decompositions will give the same result, provided crossing symmetry is obeyed, and also provided C is permutation symmetric. So the statement is that if C is permutation symmetric, and if you have crossing symmetry, then you can compute any n-point function on the sphere, in the sense that any decomposition will give the same result. And the reason why the higher correlation functions don't give extra constraints is that actually this crossing symmetry already implies that your operator product expansion is associative. So if you want this, this operator product expansion, well, it should be associative as a consequence, actually, on the axiom of commutativity of fields. So, the commutativity of fields implies that the OPE, well, it should also be commutative. Is commutative and associative. Well, associativity just means that I could do this operator product expansion, or I can do this one, and the result would be the same. But once you know that the operator product expansion is associative, then it's fairly clear that your n-point function, that you can consistently compute an n-point function, and that the result does not depend on the order of the operator product expansions. Okay, a question? Yeah. So if there are no questions, I will conclude by defining, actually, a conformal field theory. So a definition of a conformal field theory now is a spectrum S and a 3-point structure constant C, well, invariant under permutations, that obey crossing symmetry. Well, that would be the definition of a conformal field theory actually on the sphere. If we want conformal field theory in higher genus Riemann surfaces, we'll have extra constraints, and we'll talk about them later. So that's the conformal field theory in the conformal bootstrap approach. And then let me define what it means to define. So to define a conformal field theory is to give some principles for determining the spectrum and the three-point structure constant. And we'll see examples. For example, we can define minimal models as the conformal field theories whose spectrums can be decomposed into finitely many representations of the Virasoro algebra. And it turns out that this is a good definition for minimal models, but this does not give us the solution, or this does not compute the correlation functions. So to solve now a conformal field theory would be to actually compute them. To actually compute the spectrum and the three-point structure constant. And that's what we will be doing in the cases of minimal models and Liouville theory. Yes?
Just one question. Having something like the stress energy tensor is not, that's not part of your definition, right?
Yeah, so the question is whether the energy momentum tensor is part of the definition of a conformal field theory. And it's a subtle question. On the one hand, I want to have an energy momentum tensor because I can build it from the Virasoro algebra. So in a sense, it always exists. But I'm not assuming that it's part of the spectrum, in the sense that if I have an operator product expansion, in principle, or if I have crossing symmetry, I'm summing over the spectrum. But I don't assume that one of these terms will correspond to the energy momentum tensor. So if it doesn't appear in the spectrum, then you can consider it as an auxiliary field if you want. And that's what we will have in Liouville theory, actually. Yes?
You still assume conformal symmetry.
Yes. So the question is whether I'm still assuming conformal symmetry. Yes, I'm assuming conformal symmetry, and this is implicit in this definition, because when I say that we have crossing symmetry, the crossing symmetry equation involves conformal blocks, and the conformal blocks are just expressions of conformal symmetry.
Even if you solved in that sense the CFT, and I ask you what is a 5-point function of something, that's still, it's sort of a bit implicit, right?
So your question is can I compute the 5-point function if my CFT is solved in principle?
Or whatever, higher point.
Yes. So the answer is, in principle, I can't compute them, although the best way, the most efficient way to compute conformal blocks is numerical, I would say. You have analytic formulas for conformal blocks, but they tend to involve large sums over Young diagrams or such things. So they are not necessarily very practical. If you would like to compute numerically, you can certainly do it. Although if for a 20-point function, probably the computations will be quite slow. But you can do it if you have a large enough computer. Yes?
Return to the operator product is fine. So the OP coefficients are determined by the particular dynamics of the theory, or determined by the representation of the Virasoro algebra in which the fields are written, or how can I find them explicitly in a given context?
So your question is how to compute the OP coefficients, or the structure constants, basically.
Yes, so in this case, the OP coefficients.
Well, the OP coefficients, in the bootstrap approach, you compute them by solving crossing symmetry. And that's what we will do.
So they arise from the particular dynamics that they have. If I change the action, I change the OP coefficients.
Can I make a comment? So first of all, this equation that is written there, the OP coefficient, this is an off-shell. So this is your previous question. That's a completely off-shell equation.
Off-shell?
Yes, completely off-shell. Now, the reason why we cannot do what you said is that usually we don't know the C's
We just don't know what they are. And the way we compute them is we take the operator product expansion, we write down the crossing equation. If we are smart enough, we solve it, and that's how we find them.
So in which sense this should be an off-shell?
This is a true equation that holds at the level of operators. You don't have to insert it inside the correlation function for it to make sense. It's an abstract algebraic thing that when you have conformal symmetry is actually also convergent. So that's a theorem.
Yeah, I would add that the correlation function you have determines the radius of convergence typically, but it should always converge in some region.
Yes.
Something that I often wonder, so you say that you need to know the spectrum and the structure constants. Are there examples of two theories that have exactly the same spectrum but different structure constants and they are both meaningful?
Yeah, that's a good question, and I don't know an example, I must say. Because these crossing symmetry equations are really, strong nonlinear equations, so if you have the same spectrum, typically you get the same structure constants, but I don't think it's a theorem.
I'm also unaware of any counterexample. So.
Yeah, that's a good question, but I don't know a counterexample.
I have a question.
Yes?
So in this definition, you don't include the central charge, right? Because you say you don't include the straight tensor in the spectrum.
So your question is, what is the role of the central charge?
Yes,
yeah.
It should be the OBE coefficient.
No, so typically the central charge appear in the conformal blocks. So conformal blocks are functions of the central charge. So you don't see it in my formulas for conformal blocks because I only wrote the first non-trivial coefficient. But starting from the second non-trivial coefficient, you have an explicit dependence of the conformal block on the central charge. So then if you define a theory where the central charge is a parameter, such as Liouville theory, for example, where the central charge can be basically any complex number, then of course the OP coefficients will depend on the central charge. Yes.
Sorry, maybe another thing. The conformal blocks, another way to understand what they are is that they are solution of the quadratic Casimir of the, so you can make the quadratic Casimir of the conformal symmetry, and acting on, finding solutions of this thing gives you these conformal blocks. So you can really calculate them all the way. So they are completely known even if he didn't write them down yet. And they are function of C because the conformal algebra will have, he wrote the Virasoro, it has C in it.
Yeah, well, we'll see examples of this in a relatively simple context. So the generic conformal blocks are really complicated correlation functions, but next time we will consider 4-point conformal blocks where we have one degenerate field, and one at level 2. And in this case, as we saw, we have a second order BPZ differential equation, and the conformal blocks have to be specific solutions of this equation, and we will write really explicit formulas for conformal blocks in that example. Okay. No more questions?
So let's thank Sylvain.